Hey there, everybody. Welcome back. I know we've had a nice good break from Thanksgiving. Might be springtime if you're watching this in spring, and we're probably past the Easter break, but for the when this was recorded is right after Thanksgiving. This is going to be section 5.5. This is on using substitutions to do integrals. So let's take a look at it. We have a theorem. We're going to say u equals g of x, where g prime of x is continuous on the interval. We're going to have f of x be continuous over the range of g of x, the output of g of x, and let capital F of x be the antiderivative of f of x. Then, and we've seen like when we did this before doing chain rule, this is the chain rule backwards. If you go back and look at how we set up the notes for chain rule, we had this bit right here equal that. Well, it didn't have the dx. If we had f of u, we had f of g of x. We had that. There we go. Pointing at the wrong thing. We had f of g of x. The chain rule showed us getting that. Okay? So that's how this is working. It works backwards. The idea is we need to pick the right g of x and so that we'll clean up the integral and make it nice and easy to integrate. We want this needs to be easy to integrate. And so here's an absolutely batshit crazy problem right here. Hope you're full on turkey while you're watching this. That way you'll be like, ugh. Look at this. We've got the integral. We've got the quantity 4x cubed minus 2x squared plus 3x minus 7, all to the fourth power. That's multiplied by the quantity 12x squared minus 4x plus 3. Then we got our dx. Now, we could technically multiply this all out. I don't know about you, but I do absolutely do not want to do this to the fourth power and then multiply it by that. That's just batshit crazy. We're not doing that. So what we're going to do is notice, and sometimes you have to tinker with them, but usually the thing with the power on it, there's usually something that doesn't have a power on it, or something that like it's something multiplied by it. Whatever has the power on it, the derivative is present. That's the idea. So sometimes you got to tinker around and figure out what it is. Notice if we choose this to be our u, then the derivative is 12x squared minus 4x plus 3, which is right there. Okay? So that allows us to rewrite the integral. What we do is we take this here equals du. So we're going to replace this with du right there. This here is u. So, and it's to the fourth power, so we end up with a u to the fourth power. Okay? That's how this works. Now, u to the fourth power is pretty easy to integrate. We integrate, we get 1/5 u to the fifth power plus c. Then, and this is important, it ain't about you. In fact, I love saying it that way. We're going to write that down. And I'm even going to go with ain't, because that's how we say it in English. It ain't about you. Now, we tend to say you like that, but it ain't about you means we don't want to leave a u in there. So go back up, grab u, replace it back in. We started with x, we need to end with x. Now, it may feel like a lot of work, but can you imagine multiplying this all out? Does that sound like something you want to do? No. So there are, and in some cases, we can't even multiply it out. Okay. So there's a little proof of the theorem. We're going to that's just showing an example of it. We're going to let little f, little g, u, and big F be as described in the theorem we had above. Then the derivative of big F of g of x is big F prime of g of x times g prime of x. This is triggering chain rule. But F prime, big F prime is the definition of little f. That's how it was described above. That looks funny. It doesn't even like it. Let's do that. So we're going to replace that with this right here. We're going to replace big F prime with little f right there. And now we're going to integrate with both sides. So we integrate both sides. The d dx and the dx cancel out, and we're just left with that plus c. The right side is the integral we're looking for. This left side, we were really doing the fundamental theorem in calculus part 1 here. The one you didn't like, we do that every once in a while. But this here, now we're gonna sub in our u. We got u equals g of x. So du is g prime of x dx. So that's my u. And that's my du. So I got f of u, fu du. Yeah. Fu du. That's still, the left side hasn't changed. I just brought it down. And integrating little f gives us big F. And we didn't start with u. We don't end with u. We take this, we plug it back in. And we see we get f of g of x plus c on both sides. So it does work. Okay. That's a little proof of the theorem. Problem solving strategy. We want to look carefully at the integrand. Select an expression g of x within the integrand. We want to pick this well so that it's integrable. We can integrate it. And important, the derivative of g of x needs to be present. It has to be present. Notice up here, when I took the derivative of du, I had this. This was present up there. If it's not present, it doesn't work. And sometimes it's not present, but we'll show you how to finesse it. Okay, come back down here. Then we substitute it in. We substitute both in u and du. Now we should be able to integrate the variable. So if the integral can't be evaluated, we're going to go back and select a different expression to use as u. I don't know that I have any like that in this video. I usually went down the right route. In the 6.9 video, I actually went down the wrong route. And rather than erasing everything, I left it in to show you what can happen if you pick the wrong route and what you got to do. 6.9 is on inverse hyperbolic trig functions. All right, so once we have it in terms of u where we can integrate it, we actually do integrate it. But then it ain't about u, so we get rid of u, we put it back in x. Okay? So pick u so that its derivative is what's being multiplied by what's left over. Hopefully you've left u in a simple form. Let's take a look at this. We're going to start with one that's fairly straightforward. 10x to the fourth times the quantity 2x to the fifth minus 4 and dx. Now, this is easy to expand out. In fact, I think I do on this one. But I'm going to show you how it works. Usually, look to see what shows up and what doesn't go away when you take the derivative. If I do this one and I take the derivative, I'm going to get an x cubed. Oh, wow, that's way too big. Let's make a little small pointer. There we go. I get an x cubed, and I don't have x cubed anywhere here. So that's a bad choice. So check the other one. Plus, doing it, I didn't have anything for -4 by doing it. Here, when I take the derivative of this, I end up with an x to the 4th. I actually end up with the 10 also. So we're going to set u equal to that middle one. And so when we take the derivative of that, we bring the power down, lower the power by 1. We get du equals 10x to the 4th dx. So this here shows up here and here. They're not next to each other, but they are all multiplied together. The parentheses right there are showing us that this is multiplied, everything's multiplied together. So I can move it around if I need to and put the 10x to the 4th next to the dx. But that's going to be my du right here. Then this just gets replaced with u, and there's no exponent on it, so it becomes the integral of u. We'll do this green part in a second over here on the right. We'll do that in a second. So ignore that for now. Okay. We integrate u, we get 1/2 u squared plus, and I said c2. You'll see why in a second. I'm going to show how they connect up. Here we integrate, or that's integrated. Now we didn't start with u, we don't end with u. I put 2x to the 5th minus 4 squared back in there. Okay. Now let's come over here to the right side. What I did here is I actually expanded it out. I took this and multiplied the 10x to the 4th inside. Okay. Now this is easy to integrate. Up a power, divide by the power. Up a power, divide by the power. I get 2x to the 10th minus 8x to the 5th plus c1. Now, I got this answer here, and I got this answer here, and they don't look the same to me. So I'm going to show you that they are, in fact, the same by expanding out the left side one. If we expand out this one, we get the first number squared, we get the last number squared, and don't forget you got to multiply the middle two together twice. Let me write that out. Remember, that is 2x to the 5th minus 4 times 2x to the 5th minus 4. We get a minus 8x to the 5th and a minus 8x to the 5th. That gives us the minus 16x to the 5th right there. So I multiply it out. I still have the 1/2 outside. I distribute the 1/2, and I get 2x to the 10th minus 8x to the 5th plus 8. Now this matches this. So this must match that. So they're different constants of integration the way I did it, but they're still just a constant. I can put them together as one and get the same thing. Okay? Either form works as a correct answer. You do not need to expand it out. All right? Next video, we'll come back and we'll look at doing indefinite integrals. Examples of them, which is what we've been doing. With what we set it up for. We'll do some examples in a second.